Okay, children, we are starting with class. If you remember last time, we were doing different techniques of separation of mixtures based on difference in solubility, then difference in boiling point. See, all these examples we discussed in the last class. This is based on difference in boiling point. Miscible liquids, I told you all these words. Miscible liquids means liquids are miscible means soluble into each other, like alcohol and water. And then we want to separate them. So you separate them based on difference in boiling point. This is when the difference in boiling point is very less. This is good when the difference is large, more than 20-25 degrees Celsius. But this is good when the difference is very less. Then immiscible liquids, you can use this solvent extraction technique. This kind of flask, these are called as extraction flask. Extraction flask, right? So this is another thing. This also we discussed based on density. This is based on density. Then evaporation, when you mix a volatile, non-volatile words. So when there is one substance non-volatile, another substance volatile, and they are soluble into each other, then you can do evaporation. Now, this is the last technique, chromatography. Chromatography is based on IMF. It is based on the polarity of the substance, polarity. You already know the meaning of polarity. Okay, now let's see. This is thin layer, or we can call it as paper chromatography. So basically you will be asked using this paper chromatography also. Only there are other chromatographies which are coming up, like gas chromatography, other chromatographies are there. But this is the one which is important. So I will ask questions and please pay attention and start answering here. In the paper chromatography, the base is paper, this paper. Paper, you know, is made up of like it's a kind of carbon, hydrogen, and oxygen. All of them are there. So paper is falling in the category of highly polar. Paper is highly polar because it's like starch, you know, and cellulose. Cellulose has plenty of oxygens in it. So it's highly polar, paper. And it's stationary, not moving. Paper is not moving, stationary. Now this is a mixture of two inks, orange and blue. So this is a mixture of inks, mixture. So they have given the example of ink because ink will help you in visualizing it better. Mixture of two inks. I want to separate them. So what we have done, we have placed the mixture here on this line. This line. Place the mixture here. One drop, only one drop. Small amount. Now you put this paper in a container, and in the container there is a solvent. Solvent means some solution. Solvent. Let's take the solvent non-polar. Paper is polar and solvent is non-polar. So now this is called as baseline. This one is the baseline, base. Okay, now what happens? The solvent will start rising like this. And just you have to ensure that you can make it stand on something. It should stand vertically. So this is the apparatus which is shown here. Here in this container, there is a solvent, and solvent is now rising up. Solvent is liquid, is rising up. So I'm just showing you how it is rising. So this is the solvent. As you put the paper in the solvent, solvent is rising up. It will come and touch this mixture here and dissolve the mixture in it. Mixture is now dissolved in the solvent. Now, solvent will not stop. It will keep rising up. Now, depending upon the type of IMF, these two inks, these two, which one has stronger IMF with paper and the one with stronger IMF with solvent? The blue color, this blue color is moving faster. You can see it's going up faster. It's moving faster with the solvent. So it is more attracted to solvent. Attracted to solvent means it has more non-polar character. Non-polar, right? This blue one is non-polar, is more soluble in solvent, more attracted to the solvent. So it starts going up faster. And the orange one is less attracted to the solvent, less. And you can say it's slightly more attracted to the paper as compared to blue. Yes, so the component of the mixture, Azuni, the component of the mixture which is more attracted to the paper will move slowly. Paper is stationary, but the component which is more attracted to the solvent, solvent is moving. Solvent is liquid, moving up. So the component which is more attracted to the solvent will go more up. Yes, Lisha, you're right. So orange color is moving slowly. So it means it is more attracted to the paper. Blue color is moving faster. It means it is more attracted to the solvent, less attracted to the paper. And because these are different substances, different in nature, they are not exactly same. So naturally, their attraction with the paper and the solvent is not exactly same. So based on their attraction with the paper and with the solvent, one will move faster, one other one will move slowly, and they get separated. See, separated. You started from here, right? You place it in a solvent. Solvent is a liquid. It is the one which is going to dissolve this mixture. It's going to dissolve both the components, blue and orange. It's a liquid. Liquid is mobile. Mobile or mobile, you can say. Mobile. Mobile means it's moving. This is the paper. Paper is stationary. Stationary means not moving. Whoever is more attracted to the paper will move slowly, and whoever is more attracted to the liquid will move faster. Is there any holiday today? So many students have not come. And I don't have any messages also on WhatsApp. Maybe I'll check it later on. Okay. Now, if I give you a mixture and I put it in the solvent, mixture has, let's say, three components. I'm making all the three components here. A, B, C, three. And let's say the color of the A is red, color of the B is green, and color of the C is blue, right? Now, when you put this on the paper and put the paper, this is called as chromatography paper. Chromato means color. Graphic means writing. The paper, the colors are getting separated. So when you put it on this chromatography paper, stationary phase. In a solvent, mobile phase, they start separating out, right? And here is your red, and let's say this is the blue, and let's say this is the green. So this is how they separated. You already know the color code. Can you tell me out of these three, which one is the most attracted to the paper? Which one is most attracted to the paper? Which one is most attracted to the paper? Yes, because it is the one. No, no, not A. Why A? Which one is moving slowly? B. This is B. This is A. And this is C. So which one is moving slowly? Oh, this is the mixture. Aisha, this is the mixture. So B is moving slowly, right? And A is moving slightly faster. So B is the one who is most attracted to the paper, and C is the one which is least attracted to the paper and is more attracted to the solvent. That's how we can separate a mixture based on the difference in their attractive forces with the stationary phase, the one which is not moving, and the mobile phase. What is the stationary phase here? Paper. What is the mobile phase here? Solvent. And you can change the stationary phase and the mobile phase, and the name of the chromatography will change. Like here, this is called as column chromatography. Very popular. In this column chromatography, you are using a burette. This is a burette which we are using in the titrations. Titrations, we are using these kind of burettes. You can see you can open from here and the liquid is start coming out. This burette is filled with a kind of zeolite, a kind of material where is porous, material is porous, but is solid. So it is packed by a kind of, like generally we are doing with alumina, like this. Like this, right? So this is a stationary phase, it's not moving, it's solid. Then mixture, you added the mixture here. This is the mixture which you want to separate. Now on this solid stationary phase with the mixture, you are adding the solvent, the mobile phase, the solvent. Solvent, we are selecting the one which can dissolve all the components. So you can see three components here in the mixture. As you dissolve, as you add solvent, solvent in the mobile phase will moving faster down, down the column. Stationary will be the one which is not moving. Now tell me which one is more attracted to the mobile phase. See the change? Which one is more attracted to the mobile phase? The green, the red, or the blue? The solvent is moving faster down. So the green, red, or blue? The green, this one. Afan, try to answer. Green. And which one is more attractive to the stationery, the packing material here? The blue. This is based on the difference in the attractive forces, right? Now the green one will come down first. You open this tab, and you will see, take this test tube, and the green is, this is called as eluted out. The green is getting eluted out first. Then remove it, put the another test tube, then collect the red one, and then put another test tube and collect the blue one. So based on the difference in attractive forces. So what is the stationary phase here? The column, the chromatographic column. Column is packed solid material. It's not a paper now, it's a column, packed column in a burette. We are clear about it? Then we have gas layer chromatography. In the gas layer chromatography, there is a gas here. See this gas. This gas is the mobile phase. Mobile. It's moving. And the gas is moving in this kind of your metal tube. This is metal tube. Long metal column. It's a metal column. It's a tube. Basically, there is space here. Okay, now the mixture is added here. Mixture. Sample. Injected here. The gas is forced from this direction. The mixture and gas, they mix together. And then they are carried through this metal tube. Now, based on the same kind of thing, the one which is more attracted to the gas will move faster with the gas. The one which is less attracted to the gas will move slowly. And then there is a chromatographic data which we are getting with the help of computers. So gas layer chromatography is the latest thing. It is used to detect even a small amount of contamination in the mixtures. Like you want to see what all is present in this mixture. So people are doing gas layer chromatography to identify different components. Even a small amount, traces of the other compound can be detected. We are okay with the gas chromatography? So these are the different, but the principle is the same. There is a mobile phase, there is a stationary phase like this. Now, few more things related to chromatography. If you remember when we started doing the chromatography, I said put a line. We call it as baseline, right? This one. I'm going to put a line here. This line. This line here. Put your mixture here on this line. This is called as baseline. Now the mixture, the solvent is traveling and is going up to certain height, up to here, right? This is the distance traveled by solvent. The solvent here, this solvent has traveled this distance. So the topmost line is called as solvent front. See, solvent front. This line is called as baseline, where you put the mixture. You're going to measure the distance from this baseline to the solvent front. How much is that? B in this example, CB. B is the distance from the baseline to the solvent. This is B. And this is called as distance traveled by the solvent. Any confusion? Then the distance traveled by different components, like the mixture, this component has traveled this much distance. How much? A. So A is the distance traveled by the component of the mixture. A divided by B is called as RF value. RF value. R means retention. F means factor. So it's called as retention factor, RF. What is the RF value? It is the ratio of the distance of component over distance of the solvent. Agreed? And this RF value is like a fingerprint. Fingerprint. Like we have fingerprints and we can identify the person. You can identify any component, any chemical by its RF value. If somebody says RF value is 0.95, you'll say, oh, carotene, like this. It's a fingerprint. That's why it's so important. Now look at the RF value. What is happening to RF value? Is it increasing or decreasing? 0.45, 0.65, 0.71, 0.95. Is it increasing? It's increasing, Nisha. See from here to here. Always look at the arrow. So I want you to check from this to this. If RF value is high, then the attraction is more with the solvent or with the paper. Check. Carotene has the highest RF value. Is carotene more attracted to the paper or to the solvent? Mhm. To the solvent, yes. RF value is high means more attraction with the mobile phase. More attraction with solvent. Solvent is the mobile phase. And less attraction with the paper. Less attraction with stationery. So please understand this and then we are ready for the questions. So chromatography is done. Ready for questions? Okay. These are the questions based on all techniques. Difference on the solubility, difference in the boiling point, volatile, non-volatile, is based on all different techniques which we have done. You want to recover KNO3 from aqueous solution of KNO3. Means there is KNO3 ionic compound mixed with water. How to separate it? This is non-volatile. It will not convert into vapors and this is volatile. So which technique? Based on this difference, which one? Right? You take this mixture, this solution, heat it strongly, and all the water will evaporate. And what is left? KNO3. So these questions are very simple. But sometimes these simple questions, we are unable to recall how to do it. Right? KNO3 is ionic compound. Ionic compounds are, this is ionic compound. K plus, NO3 minus, ionic. All ionic compounds, they exist in solid form. They are non-volatile. They have very strong attractive forces, plus minus. So they don't get converted into gas. Afan, your answers are not coming. You're here, but start answering. Can you answer this question? So which substance Look at this. Yes, Naisha, good. So which substance, look at this solubility curve. Which substance is showing you the biggest difference in the solubility from the range of temperature 90 to 30? 90 is this, 30 is this. Which one? KNO3? Yeah, B is the answer. Yes, good. Because you can see that rest all are not showing you much difference. The solubility is changing, but not as much as KNO3. So that's the technique can be used to separate KNO3 just by decreasing the temperature. Okay, now this is chromatography. Read the question. See solvent front, this is baseline. So these are two components. Let's say this is A, let's say this is B. So which one is more attracted to the paper, A or B? B. And paper is polar or non-polar? Paper is polar. Now read the question. Using 50% ethyl acetate in hexane as the mobile phase and silica gel is there on the paper as a polar stationary. Paper is made up of, actually, we discussed the paper, but actually when I was of your age in the school, so our teacher used to give us a glass slide, glass plate kind of thing, rectangular in shape, and then we used to put silica gel on it. You make a paste of silica and then put the silica gel on this glass plate, dry it completely. We used to dry it completely. Now, this silica gel, which is actually SiO2, is quite polar, very polar. Now, this is not paper, this is silica gel. So, I think this example they have picked up from there. Now, we are not using it much. So, this is silica gel, which is polar, and the solvent is this, right? So, on the basis of chromatogram and the information, which of the following would be best way to decrease the distance that the products travel up the plate? Can you see that products are traveling quite high, right? They want the product to be slightly closer here. This is polar, right? Okay, let me tell you this also, which they will give you the information. This is also polar. Actually, it has plenty of oxygen, C2H5, COO, CH3. So polar, this is polar. So would you like to increase the amount of polar solvent more or less? You want them to travel less. You want the thing to be here, right? So you want to increase the attraction with the polar thing or you want to decrease the attraction with the polar thing? Answer this. No, Azuni, you want to increase. If you increase the attraction with the polar thing, then it will move slowly. Your silica gel is polar, right? The stationary phase is polar. Read this line. So you want this substance to move slowly, right? And in the solvent, you are using ethyl acetate, which is also polar. And you are using hexene. Hexene is C6H14 hydrocarbon, non-polar. Now the question is, would you like to increase the amount of this hexane or would you like to increase the amount of this acetate? That's the question. Think about it. The solvent has two components. One is polar, other one is non-polar. And the silica gel is also polar. You want these components to move slowly. If you want this component to move slowly, then you increase the polarity of the solvent. So, C is the answer, right? Naisha, you have any questions? You joined late today. Okay. Now read this question carefully. Is it visible, children? Question is visible? Okay. Two solid pigments. Pigment means color substances. One is blue, one is yellow. Which of the following lab setup will help you in separating them? This is filtration, this is distillation, this is chromatography, paper chromatography, and this is your column chromatography. You want to separate and collect them. Collect. Is this paper chromatography helping you in collecting them? Which one? D. This is also chromatography, column chromatography. But here, the blue color or whatever color is coming out first, you can collect it in the beaker. Here, you cannot collect it. They will be on the paper and you cannot remove it, right? Give me 1 second, please. So think about of this question and I'm moving on the next slide and I need only 1 second. Check this. So there is butyl acetate and there is ethyl acetate. So don't you think the polarity is nearly same? This has dipole-dipole as well as LDF. Both the forces are there. This one also has dipole-dipole and LDF, right? Now, which one has more stronger LDF? Because dipole-dipole is same. So I'm not comparing this dipole-dipole. So what I'm comparing? LDFs. I'm comparing LDF. Which one has more LDF? Please answer it fast. Which one has more LDF? LDF depends on molar mass, children. What happened? We are still doing unit 3. So it means this compound has more LDF, more. Because this one has a longer chain. Can you see more atoms? And this one has less LDF. So based on that, we can separate them. They have different boiling points. That's what they are saying. And you are not breaking any bond. These options are totally wrong. This one. During melting, boiling, fusion, sublimation, we are not breaking any chemical bond. So as it is straight away, you have to rule out these options. There is no breaking of CC bonds or CH bonds, just breaking of the IMF. So either B is right or D is right. So which one is right, children? B or D, Ariba? Which one is right? B or D? which one is giving you correct explanation? This is ethyl acetate. Yes, B. B is right. Ethyl acetate has shorter carbon chain, means less molar mass, so weaker LDF. So please analyze these type of questions. Last question, children. The paper is moderately polar, not very polar. So, and what is this solvent? Is it polar or non-polar? This one? Hydrocarbon. All hydrocarbons are non-polar. Yes, it's non-polar. Paper is slightly polar. So which one is more attracted to the paper? So which one is more polar? Azuni. Y is more attracted to the paper. So Y is more polar than X. C is the answer. Oh, D is the answer. Ariba, Afan, Naisha. Why? Disha, you're also wrong. Which one is more polar? Y or X? Y is more attracted to paper, moving slowly. So Y is more polar. And X is less polar. These are free marks in the AP exam. Free response questions. Not free response. Generally, they are in the form of multiple choice. But the language will be more simpler. Like here, the language is slightly more complicated. So it will appear in the form of simple question. And if you have some background of the chromatography, some understanding, you can answer it in. You have to have very clear thinking. So practice more questions. So that's the, I think, is the last question from this topic. Yes. Starting with the last two topics. One is this 3.11. There are three topics which we have to cover. One is electromagnetic spectrum understanding. Second is photoelectric effect. Third is Beers-Lambert's law. Beers-Lambert's law is experimental lab-based questions for AP exam. It's a lab which all schools are going to do. You people are going to do it in the school. Ready? So first, let's try to understand the meaning of electromagnetic spectrum. I must have given you this introduction in unit 1 also when we were doing electron configuration, but I'm going to repeat few things. So what is electromagnetic spectrum? The light which we are receiving from sun, this light, sunlight has two components. One electric, electric component, other magnetic component. So can you see the electric component and magnetic component of the light? Light is like a wave. Sunlight is coming like a wave. So this wave has two components. One is electric field, electric component, other is magnetic field, and they are moving perpendicular to each other, perpendicular. Can you see the magnetic component, green one, the green plane, this one, and the your magnetic component is here, and the electric component in this perpendicular one, the gray one. These are perpendicular to each other, and this is your. So they are moving perpendicular to each other, and this is called as electromagnetic wave. We have nothing doing in chemistry about this. But when we use the word electromagnetic, then you must have this why they are calling it as electromagnetic. So that's why I'm giving you this background. Otherwise, this is physics. Light, which we are receiving from sun, is called as electromagnetic waves. They are electromagnetic waves. They have electric field and magnetic field. Okay. Now this light is traveling with a speed. Waves, they have speed, right? All the waves, they have speed. And speed is defined as distance over time, right? The speed of light is fixed in vacuum. If you change the medium, there is some change, very slight changes. Otherwise, we are generally going to take the speed of light like this. It's represented by small c. This is the speed of light. We are okay with this? Okay. So memorize this value because you are going to use it in many questions. Now, if we talk about a wave, wave has some characteristics associated with it. One is wavelength, lambda. Lambda is wavelength. What is a wavelength? It is the distance traveled between two identical points. Like this is going up. Where is the exactly same point? Going up, going up. Not this one. It's going down, right? This one. Going up. This is a wavelength. Wavelength. Distance between two identical points. If I put a point here, over here, then how to measure the wavelength? Is here, right? This is wavelength. Naisha, you getting it? If I put a point here, where is the identical point? Going down. Identical going down. This is going up. This one. This is a wavelength. Represented by lambda. Lambda is a Greek letter. Wavelength is the length. What is the SI unit of wavelength? SI, meter. It's a distance, right? And distance, SI unit is meter. But wavelength, we are working only in nanometers or picometers like this. Generally nanometer. Because meter is too big for wavelength. So we should know the relation between a meter and a nanometer. Yes, any one of you? 10 raised to power 9 nanometer. Yes, wavelength is the distance. It's not a cycle. It's a distance traveled between two identical points. Wave is a pattern of, it's a repeating pattern. Particles are going up, down, up, down, up, down. That's a repetitive motion. And wavelength is the distance between two identical motions of the particles. Azuni, you're getting it? It's the distance. And the units are meter and nanometer. Please write on this. Okay, now wavelength word is clear. Wavelength is clear. Now I'm showing you two waves here. Okay, so this is one wave in 1 second. And this is another type of wave in 1 second. So in which case, let's say this is A option and this is B option. In which option the number of waves are more per second? More waves per second. B. This number of waves per second is called as frequency. So what is frequency? Wavelength is defined as distance, right? You can call it as distance of a wave, of a wave. And what is frequency? Frequency is called as, yes, Afan, frequency is number of waves per second, per unit time. And time can be measured in seconds, right? Number has no units. So frequency is represented by this cursive V, small v. It's a Greek letter again. So don't make it like this. Generally books are writing like this, but it should be like this. That's fine. You can do error in this representation. That's not a problem. So So what is frequency? Frequency is number of waves per second. So what is the unit of waves frequency, Afan? Unit of frequency. Frequency unit. Don't wait for me to call your name, children. All of you can answer it. Units of frequency. Number of waves has no units. So just per second. You can write it like this. Or there is another word, hertz. You must have heard about it. This is the name of the scientist who worked with all these things. Per second or hertz. Then you have kilohertz, megahertz, like this. Are we clear about it? Okay, good. Now answer this question. In A and B, you can see A and B. In which case, the wavelength is more? Wavelength. In which case, wavelength is more? And in which case, frequency is more? So, what's the relation between wavelength and frequency? Are they directly proportional, wavelength and frequency? How are they related to each other? Direct, indirect, inversely. So, I can say that lambda, the wavelength, is inversely proportional to the frequency. Can I say that? Now, remove this lambda and you can place a constant. If you are using light, sunlight, then that constant is speed of light, c, in case of light. In case of something else, some other kind of light, something else, then in that case, it will be the speed of that particle over frequency. So what is c? C is lambda times frequency. What's the unit of lambda? Meter, SI unit. Frequency per second. And you already know that speed has this unit. So what's the unit of speed? Meter per second. We already know that, right? Are we clear about it? Any questions? So I have a question. So let's come back on this A and B. Answer my question. Naisha, be smart. Answer first. So which one has shorter wavelength? Shorter wavelength. B. Which one has lesser frequency? Lesser frequency. A. Very good, Naisha. And Azuni. Good, Afan. Good, Afan. Very good. Okay. Now the next question is, which wave, these are electromagnetic waves, light waves. Which wave is moving faster? Is there any difference in their speed? A and B. Is there any difference? Okay, can you tell me what is the speed of A wave? It's a light, sunlight. This is the speed of A wave. A wave has this speed. And what is the speed of B wave? Don't you think same? No one is moving faster. This is a question, multiple choice question. Just, yeah, if frequency is higher, wavelength will go down. The product will remain C only. See this equation? Product of lambda and frequency is C. And C is constant. This constant. If lambda is more, frequency will go down to maintain this constant. If lambda is less, then frequency will go up. And that's what you have seen. So this is one of the multiple choice question, Lisa. We are okay with this? That speed of the light is constant. Wavelength can be changing, frequency can be changing according to the wavelength, but speed will remain constant. Okay. So I'm taking you now on the next slide. The things which I asked here are there also. So try to answer them faster because we have already done it. You can see three different waves, A, B, C. in which case the wavelength is smallest. Wavelength is smallest, shortest. C, in which case the wavelength is longest. And I think you can compare the uh, frequencies also. You can compare the frequency. But out of these three waves, A, B, C, now answer it very accurately. I just discussed with you. Which wave is moving faster? They are light waves, light sunlight. Naisha, which wave is moving faster? A, B, C. Which one is moving faster? Nisha. Okay. Afan, what's your answer? Same. What Azuni is saying, same. Afan, your answer didn't come. It's same, right? Why same? Because they all are moving with 3.0 times 10 raised to power 8 meter per second. Speed of light is same. Is it okay? Okay. Now, before I come on this electromagnetic spectrum, I would like to discuss one more equation with you, which we are going to do in photoelectric effect. Energy, every wave has an energy because particles are moving. They are vibrating on their mean position, going up, down, up, down. So every wave has a fixed amount of energy also. And that energy is proportional to the frequency. Now, if you look at this A, B, C, and look at this equation, so can you tell me in which case the energy is highest? C, B, A, C. So can you tell me how energy is related to wavelength? Direct, indirect? Wavelength and energy. Wavelength. See, you said C has the highest energy, right? Because it has the highest frequency, but it is the shortest wavelength. So energy is inversely proportional to the wavelength, right? Yes. So we are clear about it? Okay, now you remove this proportional. If you remove the proportional, this proportional, you get a constant h, v. This equation is given by a scientist, Planck, is given by Planck. So it's called as Planck's equation. Planck's equation. And this constant which I'm showing you, h, is a constant and is called as Planck's constant. Planck's constant. And this Planck's constant has a fixed value which you need not to memorize. So 6.626 times 10 raised to power minus 34 is units are joules seconds. These are the units. This value will be given to you in the exam. This is Planck's equation. And according to this equation, this is HV. H is the constant, V is the frequency. So according to this equation, energy is directly proportional to frequency. But we already know that frequency is inversely proportional to lambda, right? We know this already. See, higher frequency, lesser lambda. If I remove this proportional, what is the constant here, Afan? What's the constant here? If I remove this proportional, C, no, this one. H is here. This is frequency versus lambda. You remember C? Remember we started with this equation that lambda multiplied by frequency is C. So whatever is lambda, whatever is frequency, all the three light waves are moving with the same speed. C is the speed of light, right? All of them are moving with the same speed. Is it okay? So this is C over lambda. So can I replace this frequency by c over lambda in this equation. So the equation becomes E equal to hc over lambda. Okay, now discuss with me. Planck's equation is clear? So please write on, all of you. Type the Planck's equation here. Planck is the name of the scientist. Type the Planck's equation. Ariba has typed. Okay, Azuni has given. Yeah, okay. Naisha, type the equation. Lisa, today's students are very less. 5 are missing. Yeah, right. So I think this is clear. If it is clear, equations are clear, let's try to understand one thing. E is equal to hv, Planck's equation, which can be written as hc over lambda. Answer my question. Very simple question based on this equation. The question goes like this. If energy is high energy, which is in this case C has very high energy. What happens to frequency? Is high or low? And what happens to lambda? If energy is high, frequency is, yes children? Are they direct or indirect? If energy is high, find this equation, E equal to hv. V and E are on the different sides, so they are direct. A V is, both of them are in the numerator. I. And what happens to lambda? Lambda will be low. So remember this. Now out of A, B, C, which wave has the lowest energy and why? Which wave has the lowest energy and why? Mhm. So look at the frequency, wavelength, which you can analyze. Yes, Azuni. Azuni is saying A. And she is right. The frequency is low, the wavelength is more. So this one has the lowest energy. And this one has the highest energy. So based on this frequency, wavelength, the light which we are receiving from sun, based on the range of the frequency, range of the energy, it is divided into different components. Like this is the sun, and this is the light coming from the sun. Some part of the light has very high frequency, very high frequency. Very high frequency means very short wavelength. So they cannot travel much in the space. Speed is same. So the wavelength is very short. So naturally they cannot reach on very close to the earth. These are called as gamma rays. Gamma rays. Gamma rays have the highest energy and the highest frequency and the shortest wavelength. So they stay very close to the sun only. They cannot reach us. So we are saved. Otherwise, gamma rays can kill us. Their energy is so high that they can break the bonds. They can break the chemical bonds of our biological system. They will break the water molecule. They will make water as H2O2. A chemical reaction starts. So everybody will die if gamma rays are there. Yeah, Bohr spectrum. We have done this, Azuni. Am I right? During this unit one, when, yeah, I remember. Okay, gamma rays. Then next is X-rays. X-rays are slightly lesser in energy as compared to gamma rays. So their wavelength are slightly longer X-rays. They also have very high frequency, high energy. They also cannot reach Earth. Earth is here. This is Earth. Do you want X-ray, gamma rays to reach here? No, we don't want. So gamma rays, X-rays, they have very short wavelengths. So they stay closer to the sun. So these are two components. Third component is UV rays. UV rays can come onto the external atmosphere. You know, Earth has a atmosphere here like this. This is the atmosphere of the Earth. And the topmost part of the atmosphere is made up of ozone layer O3. UV can come up to here and reflected by this ozone. This is UV, ultraviolet. Ultraviolet. So ultraviolet is also not entering. So these are of high energies. Gamma rays have the maximum, then X-rays, then UV. Then the one which is entering is the visible, the one which is making your word beautiful, colorful. And what else is entering? IR, infrared, heating, the one which is responsible for heat, global. Then microwave. So, and then finally, radio waves. Radio waves we are using when we are talking to each other. We are using radio communication. We are using these waves which are present around you, the sunlight around you. So we are using it, taking this help of the radio waves to talk to each other. Are we okay with this? So which one has the lowest energy? Now look at this lowest energy. Which one? Okay, the last one. Okay, now name is not clear. Okay, fine. Now check here. Check all the names. Which one has the highest energy? Gamma rays. Frequency, highest. Wavelength, lowest. And which one has the lowest energy? Radio waves with lowest frequency but highest wavelength. If you convert this in nanometer, you convert this nanometer, it is 1000 meter. It's quite big, right? If you convert this number, so radio waves, they start from here to here. This is 1 meter. 1 meter to 1000 meter wavelength is radio waves. It's a range. It's a range. Look at the range of microwaves which we are using. So now these electromagnetic spectrum has different components based on their energies, wavelength, and frequencies. Is this point clear? Now we are going to use it. We are going to use this electromagnetic spectrum in chemistry. How? Let's see. We are going to use them for the identification of the substances. Gamma rays, X rays, very strong, very, very strong. They will break the molecule. They will break the molecule. But ultraviolet and visible, they will excite the electrons. So please write down these things. Gamma rays, X rays break the molecule by breaking bonds. You're breaking bonds here. Breaking bonds because energy is so high. So chemical bonds are broken. But gamma rays and UV, they are not so high in energy, but it's sufficiently high to excite electrons. Excite electrons. So please write down. This is the next topic we are doing. So they can excite the electrons from low level to high level. Emission, absorption, the one Azuni was discussing earlier. The Bohr's spectrum, emission spectrum, absorption spectrum, that's from this part, ultraviolet visible. They have sufficient energy to excite electron from low level to high level inside the atom. You know, atom has different shells. Shell number 1, shell number 2, shell number 3. Electron is here. You make this UV light or visible light to fall on this electron. Electron will absorb the light, the energy, and will get excited. Excitation from low level to high level. Absorption of energy. But infrared, this one, this is responsible for vibrations. Vibrations of bonds. It's not breaking the bond. Like, for example, if I give you water, you already know the Lewis dot structure of water. This is water, right? When infrared rays, when they fall on this water molecule, the chemical bond will undergo stretching, bending, compressing, starts working like a spring. The bond is working like a spring. And what you can do with the spring? You can stretch it, you can bend it, you can compress it. Am I right? So chemical bonds, you consider them like a spring. And spring can undergo expansion, compression, bending. Same thing is happening here. So when IR radiations they fall on the molecules, they will not break the bonds. Their energy is not sufficient. They can only vibrate them, like a spring is vibrating. So vibration of bonds. This vibration of bonds can help you in identifying the type of the bond. Type of the bond. Like for example, if I give you C double bond O, this is a spring. Let's make it a spring like this. And if I give you C single bond O, let's make a spring. Can you tell me in which case more energy is needed to vibrate it? Yes, Lisa, more energy is needed. In which case? In C double bond O or C single bond O? One example is this, Afan. Another example is this. Can you identify which bond is stronger? This one or this one? The double. So it's difficult to vibrate. It's difficult to vibrate. So you need more energy to vibrate it. Okay. So IR radiations are used to identify the type of bonds, which helps you in identification of the functional groups. Functional means the one which is responsible for chemical nature. Functional groups. IR. IR. Ultraviolet visible, they are they can excite electrons, but generally they excite electrons only of pi bonds. So they help in identification of a conjugated system. Conjugated system. What is a conjugated system? Like for example, if I give you something like this. Oh, sorry. You children don't know the line notation. So let me make it clearly. CH2 double bond CH double single bond CH2 double bond CH. This kind of system is conjugated. It can undergo resonance. This pi bond can come here and this pi bond can go there. Like if I give you this molecule, benzene, which I think I discussed with you when I was showing you the resonance. So when we did the resonance topic, at that time, I have shown you the resonance in the benzene. There is a double bond here, a double bond here. The pi bonds are moving like this. And for the movement of these pi bonds, we need UV light, UV and visible. So this particular compound will absorb UV visible. So generally all the colored compounds, colored also because it's excitation of electron. Electron jumps from low level to high level and then they fall back. and it's in the visible range. If it is in the visible range, you can see the colors. Are we clear about it? So asking questions just for a review. We have done up to IR. So can you tell me what gamma rays and X-rays can do when they fall on a molecule? What can they do, children? Write down. I'm showing you once more. Yeah, see, breaking bonds. So see what Azuni is writing. They will break the bond, break the chemical bonds. What ultraviolet and visible can do? Ultraviolet and visible, they can excite the electrons from low level to high level. Generally, it is seen in colored objects, colored things. What IR can do? IR. Yes, Azuni, vibration of bonds. Bonds are going to work like spring. When IR radiations fall on them, the bonds will vibrate just like your spring. Spring can vibrate, right? And more stronger bond, more high energy is needed. So it is used to identify different types of bonds. Now, microwave. Okay, Afan, are you clear about the use of these three components till now? Afan, you can memorize because next part is questions only. What microwave can do? Microwave you are using in your homes, and people say, oh, don't use microwave, it can be harmful. But do you think microwave have very high energy like gamma rays or X-ray? Do you think microwaves can break the bonds? Can change the composition of your food? No. So what microwave is doing? Microwave is rotating the molecules, rotational motion, rotational, sorry, rotational. So what happens when you put your food in the microwave and you start the microwave component, the frequency and the wavelength, the molecules they start rotating. When they are rotating, they are colliding with each other. So in this manner, heat is generated. So during the rotational motion is kind of kinetic energy. As the rotational motion is there, there is more kinetic energy. More kinetic energy, we already know that kinetic energy is directly proportional to temperature. So when you are using microwaves, you are not breaking or you are not changing the chemical composition. You are just generating kinetic energy in the form of rotational motion, and that kinetic energy is responsible for heating of the food. Is it okay? Okay. And the last is radio waves. I already told you the use of the radio waves. Communication. They have the longest wavelength. You're sitting in USA, I'm in India. I'm talking to you with the speed of light because they all have the speed of light. They all have the speed of 3 times 10 raised to power 8 meter per second. So we all are talking, the sound is traveling very fast with the help of radio waves. So radio wave is used for, are they harmful to us when I'm talking? Like some people say, oh, you are using your microphone and all these things. They can harm you. But do you think radio waves are harmful, children? No. They cannot change the chemical composition. Only the headphone which you are placing on your head, if it is heavy, the posture of your sitting, looking at that screen which is bright, they are harmful. But I don't think radio waves are harmful. They are all around us. Right now, around you, all these waves are there: visible, IR, microwave, radio waves. Ready for questions? Before we go for the question, let's have a look at this. This equation I already told you. This is done. Okay. All these things done. Gamma rays break the chemical bonds. Gamma rays and X rays. UV visible excited the electrons, right? Conjugated system, conjugated pi system. This is a conjugated pi system. This one. You can see the alternate pi bonds, alternate pi bonds. So it's going to absorb energy in UV visible range. It must be colored substance. Generally, they are colored because they fall invisible, so they become colored. IR, I was talking about that stretching, bending, right? And they are useful in identification of the types of bonds. Rotational microwaves, rotation of the molecule. Then radio waves we are using for communication. In radio waves, actually, radio waves are used for NMR also. Communication is the use, but we are using for NMR. Now, what is NMR? NMR is a kind of magnetic resonance, nuclear magnetic resonance. Nuclear magnetic. Do you know, children, what is a magnet? What is a magnet? You must know that, right? But do you know that how this magnetism is created? Some substances are magnets, some are not. Do you know why? So remember one thing. Magnets are spinning. Anything which is spinning, charged particles, charged objects, particles. Do we have charged particles inside the atom? Yes. Like for example, hydrogen, hydrogen 1. In the nucleus of hydrogen, atomic number 1, mass number 1, in the nucleus of this hydrogen, how many protons are there? Only one proton. This proton is spinning. It's charged particle. It has a plus charge and it is also spinning. Spinning has two direction. It can spin up, it can spin down like this. Spinning motion, clockwise, anti-clockwise. Just like electron, magnetic spin quantum number, ms. We did the ms for the electrons. That inside the orbital you can have only two electrons, one with upspin, other one with downspin. So the spinning charged particle, electrons are also tiny magnets. Protons are tiny magnets. All of them are tiny magnets because they are spinning charged particles. So you have so many tiny magnets inside your body. Okay, but if they are paired like this, paired, one up, one down, the net magnetism is zero. But if they are unpaired, then they are definitely a magnet, right? So like hydrogen, one, how many protons are there? Only one. So that proton can be either with this spin or that spin, right? So it can behave like a magnet. So these hydrogens are like magnets. Do you think carbon can act like a magnet? Carbon 612? No, because there are six protons and they are paired. So hydrogen is going to act like a magnet. And this nuclear magnetic resonance, we are not going to go much in detail. We are just going to understand the use. It will help you in identification of the types of hydrogens in the compounds, like these hydrogens. They absorb radio waves at a particular signal. So these are called as NMRs. NMRs. These things we have to memorize because there is a limitation of explanation of these things. So uses are clear? All the uses clear? Can we do the questions? Answer this question. So what IR can do? Is it going to excite the electron? Is it going to break the bond or is it going to vibrate the bond? Pick up the answer. B. What? Who can do this part, this thing? Who can do this thing? Which component can do this thing? Excitation of electron? Ultraviolet? Visible. Who can rotate the molecule? Microwaves. And who can break the bonds? Who can break the bonds? Gamma rays. Yeah. So this is just the information. And you apply this information, memorize it, and then you can see that you can answer all these questions. Question 2. In the microwave, this is very simple question. Is absorbing in the microwave. So rotation is D. Is it D? Oh, no, 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 no. Yeah, and IR, yeah, A is the answer. Yes, children, A is the answer. So they are comparing microwaves with IR. Check this one. N2 molecule. Is the N2 molecule colorful? Is it colored? Nitrogen gas. Is it colored or colorless? It's a very general question. You should know it. Where is nitrogen gas? Is it there in the air? Yeah, it is colorless. Nitrogen gas, oxygen gas, they are all around you. Carbon dioxide. But do you see colors in your air? No, there is no color. So carbon dioxide, hydrogen, oxygen, nitrogen, water molecules, water gas, they all are colorless, right? So are you breaking the bond in N2 molecule when it's absorbing UV visible? So what is happening there? Excitation, right? Excitation is absorbing ultraviolet light. They are saying it's absorbing ultraviolet and electrons are getting excited. Ultraviolet is not visible to you. That's why N2 is not visible. Ultraviolet is not visible. So question is that nitrogen gas is absorbing ultraviolet and then excitation is taking place, but not with the visible, not with the visible, not with this, but with this. So which one has higher energy? Ultraviolet or visible? You remember ultraviolet is reflected by the ozone layer is not entering. So which one has higher energy? Yes. So they're asking this reason that ni nitrogen is colorless and is absorbing in ultraviolet for excitation of electron. But iodine is colored and it is in the visible range. See, read the question carefully. Iodine molecules absorb both visible and ultraviolet. Both visible and ultraviolet means it is visible. Iodine molecule is visible. It has a purple color. If you put it on the internet, you can see I2 crystals, beautiful purple colored. So what's the question? How to answer this question? Pick up the answer. Do you know nitrogen gas? Their Lewis dot structure? N triple bond N. This is the Lewis dot structure. Iodine, I single bond I like this. So I think Azuni is trying to answer. All of you please now pick up the answer. Everything is here. Ultraviolet high energy, visible low energy. N2 is colorless. It is absorbing only ultraviolet. I2 can absorb ultraviolet and visible. Explain why. This one? Is C the answer, children? Visible light cannot excite electrons here. Why? Because it's a strong bond, triple bond, very strong. more energy is needed. So you need ultraviolet. There is a pi bond, so electrons will get excited, but only using ultraviolet, not the visible. But here, this is a single bond, big molecule, big atoms. Big atoms, they overlap to give big bonds. So this is the big bond. So this one is easy. So here, these electrons are, they are available for excitation, these lone pairs. You're not going to excite electron from the sigma bond, but these are the one which can get excited. You're not vibrating them. Okay, option A is wrong. We are not vibrating. What we are doing, exciting. We are not removing. We are not ionizing them. Molecular mass has nothing doing. So C is the only option. Answer this question, children. Beta carotene. You heard this molecule, beta carotene? I think bio students are aware of it. Beta carotene. It's in carrot. It's good for eyes. Carrots, the name has come from carotene only, carrot, right? Or carotene name has come from carrot. It's a very long chain conjugated system, very long chain. It's bright orange or red. Why? Because it has so many pi bonds, long chain. And the pi bonds, they can be excited in the visible range of the orange color or red color. That's why it is absorbing that light and reflecting it back. It's absorbing light and reflecting back orange and red color. That's why it is orange. Answer the question. A is the answer. It is colorful, right? For this, you need one more information. The visible light, the range is 400 nanometer to 800 nanometer. If you are talking about 250 to 320, it's UV, right? And we are not talking about vibrations. We're talking about excitation. No vibrations, right? No vibrations. So electronic level, but then they started talking about vibrations. Here also this is electronic transition. So the two main absorptions are with electronic, two transitions. One is, I think, this one. This is absorption. And the one is this one. This is in ultraviolet and this is invisible. But both of them are excitation. But see, you have to rule out. You are talking about UV visible. So check how I'm going to rule out the things. I'm talking about UV visible. So molecular vibration levels is written here. So A is out. Rotational level, B is out. UV visible is just excitation. So here also molecular vibration level, that is IR, out. Now focus on C. Both of them. One is this, other one is this. Both of them are associated with transition. That's the right. This is UV and this is visible. C is the option. So these questions are very, very simple. Okay. Now I think time is up and I think we are done with this topic. I wanted to do the other one, but somehow we didn't move so fast. So in the next class, I'll continue with electromagnetic spectrum, and we'll discuss about B.S. Lambert's law and photoelectric effect. See you in the next class. Bye.